Hello, everyone. This is Dr. Young, and we are going to finally start talking about quantum numbers and these quote-unquote orbitals. This is going to be a four-part series. This part we're going to focus mostly on introducing the idea of quantum numbers and these 3D probability maps, and the first quantum number, the principal quantum number. So we've done all of this work, right? We've talked about how weird light is, how it allowed us to make these observations about atomic absorption and emission spectrum, which prompted people to think about energy being quantized, and Bohr came up with this model of an atom where you had electrons jumping from orbital to orbital to explain why certain energies were being absorbed or emitted. De Broglie came along and said, well, what if, electrons are actually like wave, they have wave-like properties. And so we are here now, right? In this video, we're going to talk about wave functions, kind of what they are on a very surfacey level, and start talking about the first quantum number, n. So back in 1925, Schrodinger created this mathematical equation that described the electron waves, right? Remember that electrons have particle and wave-like properties, that their wavelength ended up being about 20% of their size, so it was significant. And these mathematical equations that describe those electron waves are called wave functions, right? So wave functions, and they're abbreviated with the Greek letter psi. The square of these wave functions, and we're not going to get into what these wave functions look like. At some point, if you're a chemist, you might take physical chemistry and you'll learn a lot more about quantum mechanics. But for us right now, there are these wave functions. They're kind of mysterious to us. But the square of the wave function describes the probability of where you're going to find an electron, right? Because remember that because they have wave-like properties, they're not a single particle that you can just point to. They sort of have this wave-like property where they might be a little more here, might be there. The waves might interfere constructively, destructively, and they might show up in kind of funny spots. You have a probability of where you're going to find it. And these 3D probability maps were called orbitals. Now, a lot of people don't like the fact that these are called orbitals. The orbital language came from the planetary model, the Bohr model, right, where he thought that you had a center nucleus that was kind of like the sun and that electrons orbited around it. But in that model, electrons were particles that could maybe in theory orbit and kind of fly around something. But we know now that it seems like that's not the case, that they have this wave-like property. And so to say that they are orbiting is kind of a misnomer. They're not really orbiting around a nucleus. What these probability maps describe is where are you likely going to find them. So they end up looking like things like this. Like this is a map of where you're likely to find it, right? If the nucleus is in the very center, I'll draw a little red dot for the nucleus. We're saying that these probability maps here are telling you where you're going to find an electron with a certain energy. And so you have for this one, right, that for a 1s, and we'll talk about 1s, 1s, 2s, 2p in future videos, but the idea is that for a certain energy level, this is about where you're going to find the electron. It's in a kind of a circular area, right, a spherical area around the nucleus. It's not as likely that it's going to show up kind of far away from the nucleus. It's probably going to be close to the nucleus. And then if you have a different energy level, it's going to be mostly in this kind of like ring or maybe really close to the nucleus, but there's a weird little like empty spot. It's called a node where we're not likely going to find that electron. We're not likely going to find an electron like way out here or way out here if it has a certain energy level. Then you can go on and have a different energy level where you're going to find it all like above or below in sort of this dumbbell shape. But again, these are called orbitals, but it's not like there's an electron orbiting around this. It's just these are the probabilities of where you're likely to find it. That's what these wave functions being squared are trying to describe. And these wave functions can be described using 4 quantum numbers, n, l, m sub l, and m sub s. And so that's what these 4 videos are going to talk about, is we're going to go through one at a time what these quantum numbers mean. We're going to relate them to energy levels. We're going to draw atomic orbital diagrams. We're going to relate them to periodic table. How do we read the periodic table and get these quantum numbers out? That's going to be our goal for this video. So I want to kind of relate this to you. I'm going to show you this up front. Again, even though we don't really know what s, p, d, and f orbitals are yet, but I want to relate this idea of the probability map, which again was this thing over here, right, where it's just kind of like a bunch of dots and it's most likely going to be here. That we would describe that as be like, oh, well, that's roughly spherical, so we're just going to call the 1s orbital a spherical orbital. We're just going to draw it as a circle. And then it's graphically represented often like this. And this X, Y, and Z, this is supposed to be a three-dimensional axes, right? So you have your X's and your Y's and your Z's, where the Z is going straight up, the X is coming out at you, the Y is going back away from you. So it's supposed to show you kind of a 3D shape. Same thing for like this P, right? We'll often abbreviate these P orbitals as having sort of like a dumbbell shape, sometimes drawn like that, or sometimes drawn as that. But roughly, right, we were taking these probabilities and trying to make them into shapes so that they look like stuff like this. Like here's the one that looks the most like what I just drew, right? Where you have a round part up above and a round part down below. And there are different phases. We'll talk more about phases later. That's why these are different colors. You have a yellow phase and an orange phase. So we're taking these probability maps, right, based on the wave-like properties of these electrons and trying to turn them into shapes of where they're likely going to be, and we call those orbitals. Again, s orbitals, p orbitals, d orbitals, f orbitals. We're going to come back and talk about these shapes and the numbers of them more later, but I want you to have this concept in the back of your mind as we start going over the quantum numbers. Here's a big old honking table. Again, don't worry about all of this right now, but I'm going to keep bringing this up because we're going to keep on going over it. But this is the principal numbers, the four principal numbers, right? Your principal quantum number, your angular momentum quantum number, your magnetic quantum number, and your spin quantum number. And then kind of what they do and what are the allowable values. Again, we're kind of just looking at the outputs and the numbers here. We're not getting into the hardcore math, you know, the Hamiltonians or Hermitian operators or anything like that. We're just going to leave all that stuff alone. But what we're going to talk about in this video is the principal number n. What is that first principal number, right? How does it determine the energy of the orbitals, etc.? What are the allowable values? Well, I'll just mention now, the allowable values, you basically start at 1, and then you just count as high as you really want in theory. 1, 2, 3, 4, 5, 6, 7. We won't see anything really probably beyond 7 or 8, but in theory, it could go on to infinity. It could go on to infinity. So what is the principal number describing? Let's take a look. So the principal quantum number, which again is just a small n, it's abbreviated as a small n, it's sometimes called the shell number. So if you hear someone talk about the shell number, they're probably talking about the principal number, the principal quantum number n. And that's going to determine the size and the energy of the orbitals. And remember, by orbitals, I mean the probability map where you're likely to find it. And it's going to relate directly to your periodic table, right? So if I look at the periodic table, I can get my n for the highest energy electron of any element on the periodic table. And I'm going to go ahead and modify this slightly for us. Well, actually, I don't need to quite yet. The period, right? Remember your periods are here, right? So here's your first period. Let me do this in a different color. You have your first period, second period, third period, fourth period, 5, 6, 7, right? This is your period number. And what I'm saying is that the period number on the periodic table is going to also equal your shell number. So if you take a look at an element like carbon, for example, right? So we got carbon out over here. Since carbon is in the second period, an electron, the highest energy electron in carbon, is going to be in the second period. It's going to be in a 2 something level, like a 2s or a 2p. That's what the numbers are going to be. And so the principal number, right, whether it's 1, 2, 3, 4, this is going to equal your principal quantum number for that orbital. Now, this is going to seem a little like, what on earth are you talking about right now? Because I haven't filled in a lot of background details, but we're going to add this in the next video when we talk about 1s versus 2s versus 2p versus 3p, etc. What I want to mention here right off the bat, and again, this is something that you haven't quite, we haven't talked about yet, but we're going to come back to this. We're going to divide the periodic table into blocks. And I've got my friend helium out here. Helium was just put over there, right, because it has a full outer shell. It looks like the other noble gases here, right? You have helium, neon, argon, etc. But our friend helium really is going to kind of go over here in terms of electron configurations and this quantum stuff. So we're not going to have helium be over on the right-hand side. We're going to put it right next to hydrogen. Right, it's going to be right above magnesium. And I'm going to divide the periodic table into blocks. This is called the S block. The groups 1 and 2, the alkali and alkaline metals. So this is our S block. We are then also going to have what's called the D block. So this centerpiece here with all the transition metals is called the D block. The next section over here on the right-hand side, this is your P block. So you have your D, your S, and your P. And then these down here, the lanthanide and actinides, right, these rare earth metals, are called your F block. So you have these blocks, the S block, the D block, the P block, and the F block. And that'll make more sense in the next video, but I just want to tell you this now. The reason I want to tell you this now is because what I've said so far is true for most of the elements, namely that your period is going to equal your quantum number. But for the D block, your quantum number is actually going to equal your period minus 1. Period minus 1. And let me write this up here too in case that's hard to see. For the D block, your N equals the period, right, the row number that you're in, minus 1. So what that means is if you look at an element like, for example, vanadium, let's say we have vanadium right here, the third transition metal. If you look at vanadium, its quantum number, its principal quantum number is not 4, it's 3. So the highest energy electron in vanadium is not actually in 3, it's not actually in 4, it's in 3, because we're taking the period minus 1. So everything right here is in a 3d orbital. Here, this is all in a 4d orbital, 5d orbitals, 6d orbitals. So they're the period minus 1, but we're able to read the periodic table and figure that out. Ditto for the F blocks. The F blocks, their principal quantum number is their period minus 2. So keep in mind, right, that the lanthanide and actinides, so lanthanides and actinides, they get inserted right here. So when you're looking at your periodic table, and there's all kinds of different ways these are shown, but if you're looking at your periodic table, that's where they usually insert here, right? So if you're looking at lanthanum, lanthanum, it's in row 6, but we subtract 2, right? So the period is 6, but we subtract 2. So this is actually a 4F, and this is a 5F. And so we can get the period of the highest energy electron by just looking at the periodic table and looking at where that element is on the periodic table. And again, if this still seems kind of like, what on earth are you talking about? That's okay. We're going to come back in the next video and talk about S, D, P, and F, these F blocks. But I wanted you to see on the periodic table that we can get the principal number by looking at the periodic table for any given element. And again, we'll practice this more in the future. Now, with that increasing quantum number here, right, with that principal number, so again, 1, 2, 3, 4, 5, 6, and 7, as you increase, as you go down the periodic table, right, those orbitals get bigger, right? So orbitals increase in size. They increase in size, they get bigger. So if you have an orbital here, this would be a 1s orbital, you'd expect the 2s to be bigger, and the 3s to be bigger, and the 4s to be bigger, all the way down to the 7s would be the biggest of all of them. And so here's some diagrams showing exactly that, right? We would say, oh, here's a 1s orbital, here's a 2s orbital, it's bigger, here's a 3s orbital, it's bigger yet, and you would just continue going down the periodic table that way. And the same thing applies for the others, the p's, the d's, the f's. Any orbital, whatever this number is in front, right? This number in front is the n. So if you say a 1s, the 1 is the principal number. The 2, the 3. Those are the principal quantum numbers that are in front of those little letters. There's the s's, the p's, the d's, the f's. And so as you move down the periodic table, you get larger and larger and larger. And we know that also that coincides, right, with the fact that as you move down the periodic table, the elements gain more shells, they get bigger, right? You have a bigger element, you have a bigger atom as you move down the periodic table. And we'll talk more about atomic size and radius in future videos. But they just get further and further from the nucleus because you're going to be increasing in energy. And speaking of increasing in energy, as you get larger, right? Well, again, remember again that we're saying that these represent, right, these little drawings represent the probability of finding an electron. And so as you look at this, right, this is picometers. This is supposed to be picometers away from the nucleus. So how far away from the nucleus? As you get further and further from the nucleus, you increase in energy, or you have more potential energy to a certain extent, because you're moving your negative electron away from your positive nucleus, right? They want to be closer together. And generally speaking, electrons are lower in energy if their wave functions allow them to be closer to the nucleus. So as you go through this, right, since the 2s is larger, you'll notice that its average, the average probability of where you're going to find an electron is further away than it is for the 1s. And so that means this is higher in energy, right? There's more potential energy there. It's a little further away. And if you go up to the 3s, the average radius for the probability moves even further out. And so as you get bigger, your average radius moves further and further and further and further out. And so what we can say is if we're drawing an energy diagram, so here's an atomic orbital energy diagram. Where this is just increasing energy. What we're saying is that your 1s orbital is going to have a lower energy than the 2s, which is going to have a lower energy than the 3s. And you can imagine that the 4s would be even higher, the 5s would be even higher, 6s, 7s, etc. You get, as the principal number increases, your energy increases also, right? So they correspond. The larger the principal number, the larger the orbital, the larger the energy is of that orbital that's describing, whether it's a 1s and to 2s, or whether it's like a 2p to a 3p. That principal number, the number in front of the orbital, means that you're going to get further away from the nucleus and higher in energy. And that's basically what the principal number is telling us. It's the first sense we have of how much energy does an orbital have. So what we're going to do in the next video is we're going to kind of fill in some of that stuff that I was saying but not really describing quite yet, is the L quantum number, right? The angular momentum quantum number, because that's going to give us the shapes. That's going to tell us the S, P, Ds, and Fs. So I had to kind of talk about them in this video, but we're going to really talk about their shapes more in this next video. So study up. Let me know if you have questions. Watch this next video.